Welcome to the classroom. Today we're talking about metamorphic rocks. Meta being change, so metamorphism means changing rocks from one rock type into another. We can take sedimentary, we can take igneous, we can take even metamorphic rocks. We can apply heat and pressure to change them into metamorphic rocks. There are two main types. There are foliated and non-foliated metamorphic rocks. What is a non-foliated metamorphic rock? Well, that's when we take a parent rock, like this limestone that has different layering in it. Those are bedding plains that were deposited layers, alternating perhaps shale and limestone layers. And we apply heat and pressure through plate tectonics, mountain building, and so on. And we actually purify that limestone, which is predominantly made of calcium carbonate, into marble. It's a non-foliated rock because we have removed the bedding planes, we've compressed it, and we've actually grown the calcium carbonate minerals, and so they interlock better. And sometimes they have a very granular texture. Depending on the amount of heat and pressure that's applied, we may not get a pure marble, or it may not be as pure snow white as this Carrara marble. And if you know Carrara marble, you know that Michelangelo carved the statue of David from Carrara marble. But this marble here from Ontario, near where I grew up, is not as pure. It's not snow white. You can actually see some alternating layering here, but we have very large crystals. When we take a zoom in here, you can actually see the crystals of calcite with your bare eyes, and you can see they're well defined. And so we have changed that limestone into a marble. However, it's non-foliated because the original minerals that we started with are basically all calcium carbonate, and the resulting rock is also basically calcium carbonate. The same could happen with a sandstone. We could take a sandstone and make a quartzite out of it. It's all quartz, so we still have a non-foliated rock. But what about foliation? How do we develop foliation? Well, foliation develops as we apply heat and pressure to a parent rock that already has different minerals in it. When we take a granite, for example, don't take it for granted, it might be nice. This actually is a gneiss. And you can see on the one surface here, it has the alternating colors like a granite. We have potassium feldspar, and we have plagioclase and quartz. But you can actually see when you look at the end here, some layering. Now, it's very difficult to see perhaps because it's very subtle, but we have stretched out the minerals very slightly, and with the heat and pressure, it's starting to separate minerals that have different properties. For example, here in this phyllite, we have light and dark bands that have formed because they're different properties. They're starting to come together into like mineral layers. Along the way, we can grow new minerals as well. So it's very common to grow micas and biotites and garnet depending on the amount of heat and pressure and the degree to which the metamorphism has taken place. So here you can see the sparkle and shine is muscovite, and muscovite, remember, is a very thin platy mineral. And so the light glints off of that one surface, and biotite is the darker variety. But also here we have what look like almost like chocolate chips. And those are garnets that really are growing out of and along these foliation planes. So garnet's also a very nice mineral. It's a metamorphic indicator mineral. And we can get lots of muscovite and biotite growing on those layers to define schistose planes that you can sort of see in this sample. And there are lots of layers, but they're a little bit wavy, and that's pretty key for indicating a schist is a wavy layering. So here we have nice banding. There's a light and dark layering. It's very distinct individual layers, and that's what we call a gneissic rock. There's also a very interesting factor of this sample I have here, and it is this fold. And when we get enough heat and pressure, we can actually bend rocks in a plastic manner without breaking them. And that's another indicator of metamorphic rocks. So how do we actually fold metamorphic rocks? Well, let's get some layers here. We've got perhaps a sandstone, limestone, and another sandstone layer. They mark different environments of deposition. But during plate tectonics, we have a convergent plate boundary. So pretend we have another plate coming into contact with this plate, and this plate starts to bend, all right? So we're already starting to fold these layers, and if we have subduction happening and we have lots of sediment building up on this bent limb of this area, we get a lot of heat and pressure generated, okay? And we can start to fold the layers, and if we continue to press, we might get complex folding, and we call it overfolding to get lots of complex folding. We can actually trace out and figure out the stresses and the pressures and the directions that cause the folding by looking at the actual folded rocks. And that helps us to understand where we might trace out the layers and where they might exist in our geological model. And that's part of the engineering link. How do we actually bend the rocks? Because they're a hard, brittle material. The material needs to be plastic, okay? And for that, I've made some plasticine layers here, and we'll get a nice view of that. And we'll see what happens with our plasticine layers when we apply some bending forces to it, all right? And we can bend it. You can see perhaps on the top layer, there's some small cracks happening, okay? But we're stretching that layer, okay? And we're really folding it over. So you can see nice folded layering, okay? And it basically stayed intact. So under enough heat and pressure, the rock can behave in a plastic manner. Now, this set of layering, we put it in the oven for a couple of hours. So that dried it out a little bit. And I can actually feel it. It's a bit crusty feeling. And so if the layers are closer to the ground surface, the heat and the pressure is not quite as high. The rocks can be a little more brittle. And so if we bend those layers, you can see even the fractures developing. So we can still get some folding happening. On the back, you can see some cracks in the sublayers, and we have cracking across the top. But we're still folding it. We're still getting some layers bent, some are stretching and tearing and fracturing. In plate tectonics, the topmost layers, their surface, they're going to fracture and fault and break. And those deeper down, they're going to fold and bend in a plastic manner. And that's how we can get nice folded layers that are bent without breaking. That's really key for finding metamorphic rocks. We either need to look for minerals that have grown on the foliation plains, or minerals that have changed their crystal structure, but the same, maybe are a non-foliated rock like our marble, or we have our well-defined folds, or folds with some fractured rock material. That is all indicative of metamorphic rocks, and then we can understand and take that understanding to trace out where the layers may exist, where the foliations, they tell us where the rock is headed underground. So if we bury this rock up to here, we know this limb projects underground, and we can use that information to create our foundation designs and our tunnel designs. Knowing where the rocks exist underground is part of the key to engineering design, and that is the engineering link.